Okay, so picking up where we were last time. So we were talking about coordinate curves. Why we were talking about coordinate curves was not particularly revealed yet, but we'll get to that momentarily. So the idea of a coordinate curve is that if you have two variables and if you fix one of them, then the result is you have position as a function of, in effect, really only one variable. Right? And position as a function of one parameter is a parametric curve. Right? So as I have it done here, this is the S coordinate curve of that parameterization, where S remains the variable and T is fixed. Okay, so we saw an example, and then I ended with this observation that there's a relationship with velocities. I'll try to get all this on the screen. There we go. So I claim that if you look at one of these coordinate curves, let's see here, I'll do this in green as well, one of these curves, and if you take the velocity of this coordinate curve, let's just kind of think through what that means, right? If you're taking the velocity of this curve, where position is a function of only S, that means we're just going to take the derivative with respect to the only variable, namely S, with the remaining understanding that, of course, T is still held constant, right? And if you think about it, taking the derivative of the output with respect to just one of the inputs with the understanding the other variables held constant is an existing idea. That's a partial derivative, right? So the velocity of that curve is the same as the corresponding partial derivative of the original surface parameterization. Kind of cool. All right, and with that noted, we'll proceed along. And so here is again, back to the sphere. I just kind of like to have something actual concrete to work on sometimes. So we have the sphere parameterized with phi and theta. We wrote the explicit formula down last time, I guess it was. Spherical graph parameterization, rho equals 1. Right? Okay, so partial derivatives are velocities. All right, let's make that observation here. These partial derivatives here are velocities. What happens when you have a velocity? And the idea of a velocity is that if you talk about an input change of the corresponding variable, some input differential, that input differential times the velocity gives you the output differential, right? Straight out of chapter 2. And so with that in mind, if I displace by some amount d phi over here in the phi theta plane, right, there will be a corresponding differential that results in the output. In other words, if I sort of move in the in the phi direction by some teeny tiny little amount, then that'll move me along the surface of the sphere by correspondingly some tiny little amount. And again, the velocity, aka the partial derivative, is what makes that connection between those differentials. So likewise, let's see here. I'm kind of regretting my color choice there. Let me redo that color choice. So now with a change in theta, there is correspondingly an output differential that results. And again, just input differentials relate to output differentials by way of the derivative, in this case the velocity. Okay. So, cool. So we have input vectors, output vectors related, and in particular, what we're going to be interested in is if we look at the corresponding little areas. So if I look at some little piece of area over here in the phi theta space, little rectangular area, the bottom edge is thought of as a vector of magnitude d phi, and the side edge d theta, which has therefore an easy area, just d phi d theta, and then there's going to be some sort of resulting output area, and exactly what that is something we're going to have to compute. Thankfully, it's an easy computation, right? This area ds is just it's the parallelogram that results from looking at let's see here, this edge vector, which we computed on the previous page to be that, and color choices, this edge vector, which we computed on the previous page to be that. So how am I going to compute this output area ds? Well, this is chapter 1 thing, arguably a Math219 thing. It's the area of a parallelogram in space. It's the magnitude of the cross product. At which point we can take these input differentials, which are after all scalars, factor them out as scalars do, right? And altogether then I now have a nice conclusion, which is, let me get rid of all the mess here, which is this output area relates to this original input area by a simple factor, right? And we've already computed it conveniently this time, and there it is, the magnitude of the cross product of the partials of our surface parameterization. That's our, what you might call area stretching factor. In other words, if you're looking at a little piece of area over here, you look at its image over here, what's the proportion between the areas? This right here. Is everybody happy? Okay, so we are rapidly approaching the ability to actually do a new kind of integral, and we're going to, sort of slowly work our way up to that, so I don't want to get ahead of myself, but we've kind of got a stretching factor figured out. That said, there are some little notational points that I want to get sort of straightened out first. Notice that our stretching factor here is a magnitude of a certain vector. This certain vector, this cross product of the partials, it turns out it's important for a variety of reasons. And the fact that its magnitude is our stretching factor is one of the big ones, right? For reasons that we therefore already see some of, this deserves a name. We're going to call it capital N. It's pretty standard. This is what I like to call the parametrized normal vector. If you think about it, both of these two partial derivatives are tangent to the sphere, tangent to the surface, whatever your surface is. And so their cross product is going to be perpendicular to that surface. So that cross product is going to be something like this maybe. So normal vector, because it's perpendicular like so. Parametrized normal vector, because you'll notice it comes out of the parameterization, right? So it is a result. Oh, wow, I want it to be in highlighter mode. There, excuse me. Because it comes out of the parameterization. Which, by the way, is a little bit weird if you think about it. We got this surface here. We want to understand the surface. We want to understand intrinsic features of the surface. And we have this thing now, this capital N vector, but notice it's not intrinsic to the surface. It depends on how you parameterize the surface. So it's a kind of arbitrary in a way. And that's something to keep in mind. It's capital N is going to be very, very, very useful for us, but it is not the end-all, be-all. It's a very specific kind of thing. Okay. For whatever it's worth, the book calls this the standard normal vector. I'm uncomfortable with that terminology. It makes it sound like it is intrinsic to the surface. It's clearly not, right? So one could argue that this is the standard that you create from the parameterization. If you're given a parameterization, this makes a normal vector in a standard way. I guess so, but you can see how it could be misconstrued as being intrinsic to the surface. So the book will use that term. I won't, but heads up. Okay, so again, we've got this vector, and it's the vector whose magnitude is our stretching factor. And so here's kind of a rewriting of our stretching factor here, our area stretching factor. A lot easier just to call it the magnitude of capital N. Kind of convenient. Okay. All right, so let me show you how to use this to compute a surface area. So we're going to look at the unit sphere. We've got the calculation kind of mostly set up, except for some details, some, to be fair, pretty ugly little details. Right? But here's how that plays out. Given your unit sphere, we have our parameterization there again. Rho equals 1. Right? Plugged straight into the coordinate conversion formulas gives us a parameterization of the sphere. Then we take partials. Then we take the cross product. Oh, missed. I'll do that one more time. Right, so take the parameterization, take the partials, take the cross product, then take the magnitude of this, and there's a fair amount of effort that goes into computing this magnitude. You can see what we're taking a magnitude of. It seems like it's got the potential to get kind of weird, right? But amazingly, the Pythagorean identities kick in several times, right? And it turns out that the magnitude, great big expression that you start with, simplifies to just sine phi. How about that? Isn't that lucky? And I have a further comment about that I'll say in just a moment. But I want to get to the end of the end zone first, and then I'll come back and comment more in a second. Now that we have our area stretching factor, I can compute the surface area of the sphere with a pretty straightforward calculation. First, I argue that surface area, the whole is the sum of the parts. And of course it is. Take a sphere, chop it up into little pieces. The area you're looking for is the sum of the areas of these little pieces, nothing to it. We saw above that the area of each piece is stretching factor times the input areas, d phi d theta. Right, so that's just plugging in. We further computed already that stretching factor is sine phi. And so we find ourselves now just needing to do this integral. By the way, do keep in mind, since we're integrating over the entire unit sphere, theta is going to go all the way around and thus go from 0 to 2 pi. And phi, for each value of theta, phi's got to go from straight up to straight down, which is going to have phi going from 0 to pi. And we have ourselves an iterated integral. Plug and chug, it's pretty straightforward at this point, right? And here's our final answer, which we already knew, of course, but 4 pi. All right, everybody happy? All right. Okay, now a couple things I want to say. One common question that I get from students is, hey, wait a minute. Aren't I supposed to put like rho squared sine phi into there? Isn't that the rule? Right? Always stick in your stretching factor. Here's the thing. Rho squared sine phi is the volume stretching factor. That's the proportion between input volume and output volume, right? When you're doing spherical coordinate for triple integrals. That's about volumes. We're doing areas here. Area is a totally different geometric quantity. So all that rho squared sine phi stuff kind of goes out the window. It's not really directly related to what we're talking about. So that's the first observation I wanted to make. Second observation I want to address. Students, again, very regularly ask, well, hey, wait a minute, check this out. If I did say rho squared sine phi, this unit sphere has rho equal to 1. If I take that rho equal to 1 and stick it into there, then this turns into sine phi, and hey, isn't that just an easier way to come up with the same formula? How about that? Very tempting. There is an element of truth under this, right? But it's fundamentally wrong still, because it remains, this rho squared sine phi came about by looking at volumes. we are fundamentally not looking at volumes here. We're looking at areas. So again, element of truth, if I were to take a certain very critical point of view on this calculation, there is a connection between this correct calculation and this basically bogus calculation. Right? So there's a little bit of a connection there. But the thing is, this does not always work. You cannot take this formula and then just kind of plug in the formula for rho. That is not valid as an argument. And in fact, you will only even get the right answer if rho is constant. And showing that is more trouble than it's worth in a context like this. But I just want y'all to be aware that tempting though this is, it's fundamentally unsound reasoning and kind of coincidental that it gives you the right answer even in this case. And it certainly won't give you the right answer in any other case. Okay. All right. How we doing? Pausing. Questions? Everybody happy? Okay, moving along. Just a quick summary. I mean, everything that's on the screen here, pretty much we've already talked about. We have a parameterization of a certain. Again, I want it to be in highlighter mode. Parameterization of a surface for which we can talk about the various velocities, aka partial derivatives of the parameterization. We can talk about the various input differentials and the resulting output differentials. We can talk about the corresponding input area and output area and the proportion. And then we talked about the capital N vector. We also, of course, had previously discussed our unit normal vector. This goes way back, right? We've been talking about unit normal vectors for a long time. So, of course, the unit normal, a lot like the not unit normal, right? The parameterized normal. Just the only difference is the magnitude. Okay. All right. And various algebraic relationships. So again, we've talked about that and that. The only additional thing I want to point out is that this formula for our capital N vector, this is where we stopped with it on the previous page, but you could write that out in coordinates if you wanted to. Nothing to it. You could crank out that cross product in coordinates if you wanted to. So, I mean, again, you can take it further. And this is a nice little convenient shortcut, I suppose, formula for the capital N vector, if you might find that convenient. The reason I like to point this out is there's something just kind of eyebrow raising about the fact that each of the coordinates of the capital N vector are these little determinant things from when we were doing change of variables, right? And it's not immediately clear how change of variables comes up. After all, change of variables only makes sense when you're talking about a function that goes from 2 dimensions, for example, into the same dimension. This would have to be 2-dimensional, which this isn't, right? So a little bit weird that these Jacobian determinant thing come up. And that seemingly somehow change of variables seems connected to this. It turns out it really is. There's a fantastic motivation and reason for this, and in fact, it is going to turn out that this is kind of the foot in the door that's going to lead to something else later that we're not going to talk about today. So call this just a little bit of foreshadowing. Typically, of course, I think it's more natural to talk about vectors written as vectors. Coordinates are useful when it's time to plug and chug, I suppose, right? But really, the mathematical objects, the fundamental mathematical objects, you should think of as being vectors, not coordinates. Okay. All right. Is everybody good? Everybody's happy? Okay. Right. Okay, there's a nice little special case. It's worth making a note of and remembering. And that is, what happens with all this if you are looking at a graph? Now, I want to emphasize this is a special case. Not every surface is a graph. Depending on how you count, most surfaces are not graphs. Right? So this is a special case. This is not an alternative formula to instead of what we just did. Not at all. Not at all. This is a special case that is useful sometimes. Okay. So that said, in this special case, if we have a graph, we know how to create a graph parameterization. When you have a graph parameterization, the partial derivatives work out pretty nicely. Look at those very conveniently located ones and zeros. Handy. When you do the cross product, notice how handy and convenient that the elements are just the negatives of the partial derivatives of the original function followed by a 1. And it's always a 1. And then when you take the magnitude, you get this formula right here. And so this is going to be my first little stopping point. I'm going to just point out that this is a nice formula to memorize. In the cases that you're looking at a graph, if you're looking at a graph, boom, right here, handy dandy. It saves you, a certain amount of effort there. So I strongly encourage that you should know this formula for use with any graph. Okay. Now I'm going to make some further observations. This business right here is magnitude squared of the gradient, right? And don't forget, the magnitude of the gradient is how steep the graph is. And so this is another nice little point of view on it, in this special case of when you're looking at a graph. When you are looking at a graph, your stretching factor, your area stretching factor, only depends on how steep the graph is. You don't even really have to write it algebraically as a function of x and y, although, of course, if you're doing computations, obviously you do. But intuitively very valuable to realize that it has this geometric interpretation. And I'm going to show you a nice example. This is a very real-world example that I have used in the real world. So let's suppose this is a picture of somebody's house. Use your imagination, right? I left out like the windows and the aesthetic features, but this is roughly the shape of a house. And as y'all, I'm sure, have noticed, roofs consist of various triangles and parallelograms and etc., right? And look up at any roof and you're going to see a bunch of different faces, right? Okay, so let's suppose that someday you're a homeowner and you need to put a new roof on your house for whatever reason. I don't know if y'all are aware of this. I wasn't when I was your age, but now that I'm a homeowner, I 100% know this. They're so unbelievably expensive. It's massive. It's like 10 grand. I mean, it's a lot of money for a bunch of just shingles made out of tar. It's really weird that it's so expensive, but it's lots and lots of money. So when it comes time, a pretty useful piece of information to know is what's the surface area of your roof? Because that is pretty directly proportional to how many shingles you're going to have to buy, which is directly proportional. Well, there's labor and stuff, right? But I mean, heavily influential on how much are you going to be paying for this roof, right? And for whatever it's worth, I do strongly encourage double checking the arithmetic being done by other people who are the ones that you are paying, right? Because how weird, they make mistakes sometimes, and turns out disproportionately often those mistakes are in their favor, right? I'm just saying, right? It's happened to me like 3 or 4 times. So how do you compute the surface area? Now, if you were to take a high school geometry point of view on this, you could say, all right, well, first of all, I'm going to have to climb up onto the roof. I'm going to have to measure the dimensions of each one of these things, and then I'm going to have to pull out a protractor and measure these angles, right? And there's going to be a tremendous amount of measuring and a tremendous amount of calculating to compute that area if you do it sort of brute force. Much quicker is just to realize that roof is a graph. Passes the vertical line test. It's a graph of a function that's sitting over what you might call the footprint of your house. And if you want to compute the surface area of a graph, we have, again, as noted above, handy formula for how to find the surface area of a graph. You see our little area stretching factor. Our area stretching factor right there depends only on the steepness. And here's where a really convenient little fact kicks in, another little incidental real world fact about when they make roofs, and this is not an always thing, but this is an often thing, that the steepness of the faces on many houses, the steepness of those faces are the same on every face. In other words, how steep the face is a constant. Again, all exceptions granted, not all houses. It's true on my house, though. And so if that steepness is a constant, then that means that this entire expression here, this entire stretching factor, is a constant. It factors right outside of the integral. That leaves you then with only... Oh, I got the color wrong. Double integral dx dy is just telling you about the area of the footprint, and that footprint area is much easier to compute. For one thing, you don't have to climb up onto the roof. For another thing, it's typically, again, all exceptions granted, typically made up out of rectangles, which are easy to compute area of, right? So you can just pull out a tape measure and just a couple of dimensions, a little bit of arithmetic back of the envelope. You know your footprint area. If you know that slope, you know the factor, boom, you know how much surface area you've got, you know how many shingles you need to buy, etc. So neat how multivariable calculus comes up sometimes in the real world. Okay. Pausing. Questions? Everybody's happy? Okay. So moving along, section 7.2. We're talking about surface integrals, and we've been down this road before, analogous road anyway. I've got some shape here that doesn't fit the form of previous shapes for which I've defined Riemann sums, but I want to have a Riemann sum for this shape. So again, let me just remind you, what are the shapes that we've talked about doing Riemann sums for? Well, we've talked about intervals on the x-axis. That's single variable calculus Riemann sums. We've talked about areas in the plane, two-dimensional area in a two-dimensional plane. We've talked about three-dimensional solids in a three-dimensional space. We've talked about curves. Dimensionally odd, right? So maybe a one-dimensional curve sitting in a three-dimensional space. We created a whole new kind of a Riemann sum for curves, and in fact, let's see here, I've got it right here, right? We pointed out that even though this curve isn't dimensionally like really anything we've done before, we can still talk about chopping it up into little pieces, and on each little piece, there's quantity per unit size times size. Right? Same basic idea, thus leading to this idea of a line integral. Okay. Well, all we're going to do here is morally equivalent. We're going to chop up this surface into little pieces. I have this whole surface. I'm going to chop it up into little pieces, and then I'm going to add up over all of those pieces. And now, again, technicalities and in practice, how do we do that? We'll get to that in a few minutes. But just strategically, if I have some accumulating quantity on this surface, maybe I want to compute the mass on that surface. Maybe I want to count how many ants are crawling around on this surface. Maybe this is the side of a water tower somewhere, and I want to compute the total amount of rust, where there is more rust up at the top and not as much rust at the bottom for weather reasons or something. How would you add up the total amount of whichever of those accumulating quantities you're interested in? Well, again, chop it up, add it up, and on each little piece, quantity per unit area times area. Which which I hope is a reasonable suggestion. What do y'all think about that? Seem like a reasonable approach? Notice the analogy. Notice how it's morally identical to what we did, again, on curves. Chop it up into a bunch of pieces, and on each piece we're talking about quantity per unit length times length. Here, it's just quantity per unit area times area. Okay. All right. Real quick, the notation that we use for this I think is pretty believable. In fact, I'm just going to kind of wave my hands at it. I mean, we've made these kind of notational conventions previously, right? Very quickly, I will point out that, of course, you do have to indicate your domain. Your domain is the surface over which you're adding everything up. Right? Again, as a subscript, like we've done in several other kinds of integrals. And now the terminology, we call this a surface integral, I think for obvious reasons. It's because we're adding up over a surface, right? And you might even kind of get the idea of why we call this a scalar surface integral, and it's because my differential here is fundamentally a scalar quantity. That's area. Not a vector, right? It's just a scalar, just a number. And then likewise, analogously, my integrand, also just a scalar. So, scalar surface integral. Looming question, how do we compute these things? It turns out we've already done it. We already know how to compute. We didn't realize we already knew how to compute these things, but in fact, we have all of the tools necessary to compute this thing. And I just want to point out, that's where we found ourselves when we were looking at scalar line integrals. Again, brand new Riemann sum for scalar line integrals. And then we kind of made the observation that, oh yeah, we know how to parameterize a curve, and we already have formulas for the ds and the dx vector and a bunch of we'd already laid groundwork for how to do this kind of stuff. And so it was just a matter of observing what we already knew that allowed us to actually compute this. So exactly the same thing is going to happen here for a scalar surface integral. Here it is, scalar surface integral. There are these little pieces of area here, ds, for which I already have formulas. A couple pages back. All right, we talked about the area stretching factor, the proportion between the area of a piece coming out of our parametric surface versus the area that went in. And we have this stretching factor, again, already long since established. Well, long as in half an hour ago. Everybody all right? We're done. That's how you compute scalar surface integrals. Right? Let me show you an example. I'm sorry, real quick. It needs to get said. The scalar surface integral is intrinsic to the surface. It really shouldn't depend on your parameterization. You should be a little bit uncomfortable about the fact that the formula does seem to depend on the parameterization, because the parameterization is all over the place in this formula. So good news, even though it looks like it depends on the parameterization, it actually doesn't. It really doesn't. Pick any parameterization you want. Yeah, appropriately regular, no discontinuities and stuff like that. But otherwise, the parameterization doesn't matter. Okay, so let's do one. By the way, real quick, let me come over here, back here to chapter 6, where our very first example of scalar line integrals, I gave us a parametric curve and a couple other specifics, and we computed a bunch of stuff all off of the same parameterization, because whether you're computing mass or moment of inertia or various coordinates of the center of mass, whatever, it's all over the same curve, which you're parameterizing with the same function, which therefore has the same velocity, which therefore has the same magnitude, namely the same stretching factor. So much is just the same in all of these calculations. So likewise here in chapter 7, as we do our first example, notice again, we could do 4 separate calculations kind of all in parallel because they're all morally kind of the same. I'm going to focus our attention on just one of these. Let's look at the mass calculation. So again, we have a surface, mass per unit area given, and step 1, we parameterize. Again, this is the unit hemisphere, so we have an existing parameterization. Rho equals 1. Spherical graph parameterization from rho equals 1 gives us this parameterization. We already did all of this, right? We already took the partials and the cross product and the magnitude and we simplified it. Correction, I waved my hands at the simplifying. Again, I encourage everybody to take 5 minutes, right? Work out those details and confirm for yourself that magnitude simplifies like this. I think it's a good, everyone should do that once in their lives kind of a deal. And then it's kind of all over at this point. It's all details. Mass is an accumulating quantity. Whole is the sum of the parts. As mass is distributed over area, the total amount of mass is mass per unit area times area. The area on your parametric surface is stretching factor times the parameter differentials, for which we already have a formula right there. Right? Everybody okay? Don't forget one thing, again, easy to lose track of, but when you parameterize, that parameterization is also telling you explicitly what your variables x, y, and z are. So this is not just some abstract vector. These are literally telling you that's x, that's y, and that's z. So specifically, z being cosine phi is what happens over here. Now, is everybody comfortable with all the individual sort of plug-ins that I've done there? But notice it's literally just plugging in established formulas. Effectively, just as a reminder, we are pulling back through the parameterization, just like multiple other pulling back throughs we've done. And we find ourselves with a single variable integral. And so, off you go, plug and chug at that point. Now, real quick hand wave, I'm going to point out that now let's look over here at the x-coordinate of the centroid. Notice that the integral is a little bit different. This integral is a little bit different from that integral in that there is this extra factor of x there, right? So we got to figure out what are we going to do? How's that going to change everything? And the answer is not much at all. All of this stuff here, all of that, you can even see it right here. It's all of this. It's all exactly the same. Same parameterization, same plugging in, same stretching factor. It's all the same. Right? The only thing that's different is, well, we have ourselves a factor of x, which is sine phi cosine theta per our parameterization. Cool. So likewise, down here, details, good details to go through and check for yourself. Make sure you're comfortable with everything that happens here. Again, all morally equivalent. All right. And let's see here. Moving along. So our next application, adding stuff up over surfaces. Another thing that we've computed over surfaces was flux. Right, so flux is computed by this formula, and it has various interpretations. Here's the big two that we've talked about so far. Flux, if your vector field is representing a fluid flow in one way or another, If your vector field is representing a fluid flow, flux is telling you how much fluid per unit time in some appropriate equivalent sense. It's the flow rate, again, as appropriate to how the field represents the fluid. So if your vector field represents velocity, then you get volume per unit time of fluid. If your vector field represents density times velocity, which again is natural in many senses, many contexts, then you get mass per unit time of fluid through the surface. Y'all may recall that this was the picture that we drew over here, and this goes back to chapter 3, and so there's a lot of little details in there, and again, a really healthy calculation. Make sure you're comfortable with a lot of details that are valuable and good stuff to make sure that you're solid. So I would encourage everybody to go back and remind yourselves about how that calculation went. Here's the thing. There's an asterisk that I have to put on all of this. The asterisk is that there were assumptions that went into that calculation. I was assuming that my area here was, was flat. In other words, said differently, I was assuming that my normal vector was constant. Right, because I used the same normal vector for, in some sense, the whole area. So this formula that we have right now crashes and burns if your area is not flat. And tragically, most areas that we deal with in the real world, not flat. Right? So what we have here is really just kind of a starter example of how to compute flux that we're going to have to figure out how to modify. The other thing to keep in mind is that this assumes that the vector field representing the fluid flow is constant, that it's the same flow velocity over the entire area. And again, physical world, the real world, that's just not how fluids work, right? There's lots of variation. Most stuff just isn't constant. That's just the reality, right? So we're going to have to figure out how to deal with the fact that in practice, most of the time, we're going to have non-flat surfaces and non-constant vector fields flowing through them. Now, again, a real quick reminder, and I like to keep track of the analogies as we go along. Recall this when we first started talking about line integrals, and we considered the work computation. And we have this, again, very handy little dot product formula for how to compute work, but it assumes, again, the field is constant and the displacement was flat. Straight line. And so in a real-world scenario where your vector field is highly variable, like I have here, and the path that you're following is not straight, right? Then what do? Right? So we're again, a very analogous circumstance to what we've previously seen ourselves in, and I'm just going to do the same thing. I'm going to say, yeah, okay, sure, but if I were to look at some little piece, just one little piece, on those little pieces, they are approximately straight, and there's not much room to have moved, and so the vector field is approximately constant. So chop it up to little pieces is, the answer. That's the foot in the door. That's the way in so many circumstances in this course, and in the exact same way that it works there for curves, we're going to do the same. I'm sorry. We're going to do the same thing here for surfaces. I'm going to recognize that, yeah, sure, we've got this great, big, huge surface, which is not flat, right? Normal vectors pointing every which way. And it's big enough that my vector field is not constant, right? My vector field is conspicuously different across this large surface over which I'm interested in flux. And I deal with that by chopping it up into little pieces. And we will look, for example, at this little piece called ds right there. And on each of those little pieces, yeah, it's approximately flat. The vector field doesn't have much time to change, so the vector field is approximately constant. And on those little pieces, I can use our existing little convenient dot product formula. Everybody okay with that? Everybody see that's the same song, second verse, right? Slightly different geometric details. It's little pieces of area instead of little pieces of length. Strategically chopping it up into little pieces. Yeah?
This might be like a weird question, but I can understand geometrically why when you make it each piece really small, it's approximately flat.
Yeah.
But I don't understand why f would be approximately constant.
Yeah, right. Okay, so most functions, well, let's say it this way, continuous functions, right? The value can certainly change. Like my finger here is sort of tracing out a continuous function, but if I look over a teeny tiny little bit, it's just not that much time to change very much. Now it's different here, of course, because this is an area and there's kind of two different directions. So when I say small, yeah, I do have to be careful about what I mean by small. I can't have it be really, really skinny but long, right? It's got to be small in both senses, right? But with that assumed, then yeah, sufficiently small, there's just not much room for which f can change. Yeah. Everybody else? What do you think? Anybody else? Any other questions? Okay. All right. Okay. And then on each one of these pieces, I'm going to go back and talk about orientations in just a second. But just to kind of, run it into the end zone on each one of these pieces. And now this is a blown up, magnified view of a teeny tiny little piece of small area ds. I have, again, this normal vector that is over that small area, approximately constant. I have my field vector, which again over this small piece is approximately constant, and the flux through that piece, I'm just going to use the old chapter 3 formula right here. It's vector field dot unit normal times the area. And we can plug that right in to our calculation. If you want to compute the total flux, the whole is the sum of the parts on any given little piece, f dot n ds. And wouldn't you know it, what we have here is, I'm going to say loosely, and then I'm going to disagree with myself in just a minute, but pretty much a scalar surface interval. Is that cool? Okay. All right, now let's talk about orientations. Let me go back to chapter 6. Here, there is this little matter of the fact that when I hike this trail, I am going that way along the trail. I'm climbing, let's say, up the mountain, not down the mountain. And it makes a tremendous amount of difference in terms of how much work it takes to walk that path, that I'm going up instead of down, because everything's backwards. There's a minus sign on everything, right? So, if we're going to say I want to compute the amount of work, we got to be specific about which direction we're going. Said differently, we're not moving on a curve, we're moving on an oriented curve, right? So this is one of our big deal refinements. When we're talking about vector line integrals, the domain has to be an oriented curve. There has to be an indication of which direction are you going. And those indications of direction are called your orientation. And so the curve combined with the orientation is the actual domain known as an oriented curve. So we have to do the same thing over here, talking about surface integrals. If I say that I want to compute the amount of flux through this surface. Well, which direction am I interested in? Am I interested in, as I sort of am indicating here with these unit normals, am I interested in the amount that the fluid is flowing, what you might call upward through this surface? In other words, as I have it drawn, would this be considered positive flux? Or, perfectly reasonably, I mean, there's nothing magic about upward. I could perfectly reasonably be interested in downward as being the positive direction. I could be wanting to compute what I might call downward flux, in which case the vector field as I have it drawn here, this would be negative flux because the flow is going the wrong way, if you will, through the surface. So neither one of these questions is automatically right or, like morally right or anything like that. Whatever. They're two perfectly reasonable different takes. They're opposites of each other. Neither one is wrong, right? So again, you have to make a decision. You have to decide when you say flux, you have to know which direction you're talking about. You have to have established, in other words, your orientation on your surface. So we don't do surface integrals through surfaces. We do these kinds of integrals through oriented surfaces. Which direction is the positive orientation has to be indicated. And by the way, these vectors here are called the orientation unit normals. And I'll remind you, we previously had a parametrized unit normal that comes from the parametrization. So we now have actually two different senses of normal vectors through the surface. And we're out of time, so we'll call that a week. And see y'all on Monday, I hope. Some of you, anyway. All right, y'all have a good weekend.